All right, we're continuing our discussion on percentage change, which is a part of exponential functions. And we know we're talking about exponential functions because the March sisters from Little Women are still with us. This is when they're at the beach the first time before Beth gets sick. This is their happy day at the beach. Okay, so exponential functions, Little Women, percentage change part 2. And we're going to start with an example. And in this example, f of x is an exponential function. Remember, that means that it's growing by multiplying a constant number from one term to the next. And g of x is a linear function. And that means that to get from one term to the next, we're adding this constant number. And we're going to complete the table that I'm about to give you and generalize it. We're going to find the equations for the functions. Okay, so here's the table. I have my input values, x, and we're going to go from 0, 1, 2, 3, 4, 5. And then I've got f of x. Remember, this is my exponential function. And I don't know all the values of f of x, but I know some of them. And the ones that I know are, if the input's 1, the output is 0.35. If the input is 2, the output is 0.245. And the only other one I know is when the input is 4, output is 0.12005. From this information and knowing it's an exponential function, I need to fill in the blanks and come up with a formula for f of x. We also have g of x, which is a linear function. These we've known how to do for a while. The pieces of this function that I know are that when the input is 0, the output is 5. That's a good one to know because that's the initial value. And with a linear function, that's the initial value or the y-intercept. That's a good value to know. When the input is 2, the output is 8.2. And when the input is 5 on this linear function, the output is 13. Okay, that's all the information we're given. And so it's like, we're detectives. We've got to fill in the blanks and then we have to generalize. We're going to start with the linear function because it's a little bit, we're more familiar with this. So linear, let's see. Let's start by, we can calculate the slope. We actually already know the y-intercept. Remember that a linear function has to look like this. We know the y-intercept is 5. Now we'll just compute the slope. To find the slope, m equals difference of y values. So we can take really any combination of these three, 2 at a time, but we'll take 8.2 minus 5, difference of the y values, over the difference of the x values, 2 minus 0. And that will equal 8.2 minus 5 divided by 2 is 1.6. Okay, so I know everything I need to know about the linear function. I know that g of x is 1.6x plus 5. And I can use that to fill in the blanks. Essentially going, if I plug in 1, so g of 1, that would be 1.6 times 1 plus 5. It's going to be 6.6. Because these are evenly spaced values, these will be evenly spaced in a linear function. So I can just jump ahead 1.6 each time. So 5 plus 1.6 is 6.6, plus another 1.6 is 8.2, plus another 1.6 is 9.8. And plus another 1.6 is 11.4, plus another 1.6 would get me to 13. Okay, so this is the linear function. Now let's move over to the exponential function and figure out what's going on there. I know with an exponential function that I can take any two consecutive values of as long as their inputs were consecutive numbers, and just take the ratio of them, and then that'll give me the change factor. So the change factor, first of all, my exponential function needs to end up looking something like this, where this is A in an exponential function is the initial value, and B in an exponential function is the change factor. That's the number you're multiplying by to get from one term to the next. And the x and the y just stay as variables. Okay, I don't know the initial value and I don't yet know the change factor, but we're going to find the change factor right now. And the change factor is that b, and it will be this value, 0.245 over 0.35. And that will equal 0.7. Okay, so there's my b. That's a good thing. So essentially, I'm multiplying by 0.7. Again, because these are nice consecutive numbers, I can do this. 0.35 times 0.7 gets me the 0.245. To get to the next one, I would just multiply 0.245 times 0.7. That gives me 0.1715. I'll just check that I'm right in line. Multiply that by the change factor. And yep, I got the number I should have gotten. And I'll keep going and get the next one. So 0.12005 times 0.7 will get me good. So I filled in all these. I do need to find out what this one is. And essentially I need to go kind of backwards to find this. There was a number that when I multiply it by the change factor, I get 0.35. So a number multiplied by 0.7 equals 0.35. Well, what goes in this box? What goes in this box is f of 0. So I know that f of 0, what goes in this box, times the change factor times 0.7 needs to equal the next consecutive output. Needs to equal 0.35. Okay, this is the one piece I don't know, the f of 0, so that's good. I'll find this guy by just solving. So I'll divide both sides by 0.7. This cancels, and I find out that f of 0 is 0.35 divided by 0.7 is 0.5. Okay, I have everything I need for my exponential function. So f of x is the initial value, which I just found out was 0.5, times the change factor raised to the x power. So times 0.7 to the x. Okay, one important note I want to make here is, first let's draw a box around this so we know it's important. This was our exponential function from the data. Do not combine the 0.5 and the 0.7. You can't multiply those together. The reason is because this exponent is really heavily attached to the 0.7. The 0.7 has a stronger relationship with this x, meaning order of operations says that it has to be raised to this power before you can do any multiplication. So these numbers look like they want to go together, like, oh, let's multiply them and then they'll both be to the x power, but don't do that. So do not combine and say 0.5 times 0.7 equals 0.35. Don't do that. It must stay as is. And this is because of order of operations. This will be true for all exponential functions. Do not combine the initial value with the change factor, because that change factor has to stay as it is raised to this variable exponent. Okay, good. Let's do another example. This example, so before we do the next example, I want to make an important note. We do not always know data points in increments of 1 for the x value. So we do not always know data points in increments of 1 for the x value. So we have to come up with a strategy where if we had something like, say this was our example, we have only 2 data points of an exponential function, 0 as an input, and say 629, 362 as the output. And then we also know that 5 as an input yields 778025. And we know f of x is exponential. And we want to find, what is f of 4. This time, we can't use the old strategy that we used before to find the change factor. There is a formula for change factor that we're going to use, and this is a more general formula for change factor that we'll use. Okay, say you have 2 data points, x1, y1, x2, y2. This is the general formula for the change factor. And it comes from, it builds on the way that we were doing it before, but you're sort of stripping away each step along the way. So we have to, in other words, to get from 0 to 5, we were multiplying by the change factor 5 times. And so in order to go backwards, we take this, we're going to take a root of the change factor, in this case a 5th root, because it was a 5th power as we were building it. So we're going to take a 5th root to unbuild it and discover what it is. So that's what this comes from. This ratio is just a ratio of your y values. So this is a good general formula for change factor that you can use anytime you have at least 2 data points in an exponential function. This is similar to how we can find the slope in a linear function between any 2 data points. They don't have to be consecutive. Okay, let's try this out. So in this case, b will equal, let's see, y value 2 over y value 1. So 778025 over 629,362 raised to this power, which is 1 over the difference of our x values. Let's see, that's x2 minus x1. That'd be 5 minus 0. So this number, I'm going to use my parentheses, 778025 divided by 629,362 raised to the 1 over 5 minus 0. Well, that's just 1 over 5. 1 divided by 5, again using parentheses for my exponent. Here's my change factor, 1 point, and I'm going to use a lot of decimals here because these numbers here are so big that there's a lot of decimal places are important. 1.043323, we'll say. Okay, this is B. And so I know, And so I know in general, this is my change factor. This was my initial value because luckily they gave us, when x is 0, the y value. So it turns out f of x equals 629,362 times our change factor, 1.043323 to the x. That's our general formula, and we'll do the thing that they asked us to do, which is find f of 4. So f of 4 is 629,362, 1.043323. Let's see, x value is 4. And when I put that into my calculator, I get that f of 4 is 745,719.7, which seems reasonable. It's close to what the output of it's close to what f of 5 is. I just want to highlight the fact that with this formula for the change factor, we can calculate that change factor from any two data points. They don't have to be successive. So not necessarily successive. And so that's pretty powerful because now we can know how to find that growth or decay factor based on just knowing that a function is exponential and knowing two data points. Okay, we have a few more things to talk about in this video. Before we go any further though, if you will message me on Canvas your favorite color, you can have 2 extra credit exam points. I want to reward people who are actually watching these videos because I know you're putting in the time. All right, percentage change part 2. We still have the March girls at the beach. And we need to talk about some vocabulary to make sure that some confusion doesn't creep in here. One way to describe change in a function is percentage change. We haven't talked about this yet, but this is a common way that you'll see a setup for a problem. This is closely related to the change factor, but it's not the same thing. Our change factor B of exponential functions. And we want to see how they're related. So before we look at some examples, I want to highlight that any function with a constant percentage change is an exponential function. Even if it's not explained explicitly, when you see a constant percentage change in a problem, you know you're dealing with an exponential function. So first I'm going to give a definition and then we'll look at 2 examples. If B is the change factor that we've been talking about of an exponential function, then I'm going to give you this formula, B equals 1 plus R. And R, I haven't even told you what that is yet, but I'm just about to. So B equals 1 plus R, where R is the percentage rate of change. So for example, so B equals 1 plus R is kind of important here. So example, and this is our 3rd example in this video, even though I didn't list 1 and 2. A stock account begins with $800. So a stock account begins with $800 and grows at 7% a year. Find the function that models the value of the account over time. Find the function that models the value of the account over time. Okay, as I read through this, when it's growing at a constant percentage. So we have this constant percentage change. This definitely is an exponential function. This is how exponential functions look. This time, I'm going to use some different variables though. The value of my function. They asked me to come up with a function that gives value over time, models the value of the count over time. So time is our input. So V is going to equal A, B, T. I just have to find my initial value and the change factor. And it looks like I have got some good information here. So when it says it begins with $800, you probably already figured out this is definitely the initial value. So that's just sitting there. And grows at 7% per year. Okay, so I asked myself, is this my B? No, but it's close to it. First of all, this tells me that it is going to be an exponential function. And this is actually R, the percentage rate of change. This is my R, so I know R equals, and I won't use 7% because when we start moving percentages into equations, we put their decimal representation. So I know R equals 0.07, but this formula demands that I use the change factor B. So B equals 1 plus R. So B will equal 1 plus 0.07, and that's 1.07. Okay, so I have my A, my initial value, and I know now what my change factor is. It's 1.07. So V, which is a function of T, is 800 times 1.07 to the T. This is the function that models the value of the stock account. Should I put this 800 and 1.07 together, multiply those? No, absolutely not. We can't put those together because 1.07 is first devoted to this exponent here. It's linked there, so we don't want to combine those. This is how it is. Okay, example 4. Kind of another simple, more simple example as we're tiptoeing into exponential functions. A $15 shirt is discounted 3% every day. Model the price of the shirt. In other words, come up with a function. Model the price of the shirt as a function of days. So this time we want, they're asking us to come up with a function that is the price of the shirt, and T is going to be days here. Okay, same story. P equals A, B, T. The price of the shirt is, I know it's an exponential function because we're getting this constant percentage change. The question is, what's my initial value and what is my change factor? So on day 0, my initial value, the shirt is $15. So this is A, our initial value. It's nice. 15. Now the change factor. Okay. This is where we have to be a little bit careful because of this word right here, discounted. So is the price of the shirt growing or is it going down? It's definitely going down. We all know that just common sense wise. We know the price is coming down. It's discounted 3% every day. So this R is not 0.03, it's negative 0.03. It's going down 3% every day. Okay, I can't put my R here. I need the B, and I use this formula. B equals 1 plus R, which is negative 0.3. And if I put this in a calculator, 1 plus negative, 0.03. Yeah. 1 plus negative 0.03, the answer for this is 0.97. This is my decay factor. It's less than 1, so I call it a decay factor. And so that's going to go in right here. Good. Let's just find out after the first day what the price of the t-shirt is real quick. So 0.97 to the 1 after the first day times 15, and it's $14.55. So after the first day, the price of the shirt is $14.55. That makes sense, that 3% discount.